In this video, we are going to be looking at logistic population growth. So with this information, how exactly do we know that this is logistic population growth? Well, first of all, I give you a K, right? The only time that you would ever see K, carrying capacity, is if we are looking at logistic growth. So that is a dead giveaway here. Okay. So what do we want to know? Given this carrying capacity, given this growth rate, and given this random population size. Okay, I can tell you first and foremost that this random population size isn't actually going to help us figure out either of these two questions. Okay, so a little tricky there, but knowing what information you need is another part that is really important in understanding this content. Okay, so at what population size, n, so we're looking for an n, will the population show its maximum rate of growth? Right, so we're not talking about the growth rate, we're talking about the population size when the population is growing the fastest. So if we look at our list of equations here, all the way down here at the bottom, we see n equals k over 2. Okay, the population size with maximum growth, right? So when the population is growing the fastest, this is how big the population is going to be. Okay, so this is the one that we are going to start out with. So our equation is n equals k over 2, okay, which is 75,000. Okay, that's the carrying capacity, and half of the carrying capacity is 37,500, and we're talking about European starlings. Okay, an invasive passerine or songbird. Okay, so 37,500 is the population at which the maximum growth rate is achieved. Okay, so from there, we can actually use this value to calculate what is that maximum population growth rate. Okay, so now we want to know the dNdt. How quickly is the population growing at this particular population size? Okay, so if we go back to our list of equations, we can see the population growth rate. And so ultimately, the population size that has the largest growth rate, the fastest growth rate, we just calculated. Okay, so let's write out this equation. dNdt, okay, so essentially the population growth rate at which population is growing. The number when the population is growing the fastest times 1 minus that same population size over the carrying capacity. Okay, I tell you in our problem here that R equals 0.31. So 0.31 times the number that we just calculated. Okay, so this is when the population is growing the fastest. So 37,500 starlings times 1 minus that same population size, 37,500, over the carrying capacity. Okay, and so if you look at this equation enough, you'll notice that no matter what, if you are calculating the maximum population growth rate, okay, this portion of the equation right here is always going to be 0.05, right? So if you're in a bind, this is always going to be 0.5. Okay, so 0.31 times 37.5 times 0.5 should give us a population growth rate, which is the maximum population growth rate, of 5812.5. Now I tell you to round to the nearest whole number, right? Because you can't have a half starling, not a live one anyway. And so the best answer would be 5813 starlings. So essentially starlings are added to the population in a year when the population is growing the fastest. Okay. Let's try a different one. Okay, so that is our starling population. Let's try to look at blue azure butterflies. These are Pine Barrens natives. Once again, we want to find the population size when it is experiencing the maximum rate of growth. So we know that n equals k over 2. So we know that K is 15,000 from our problem here over 2. So when N, right, when the population size is 7,500 butterflies, that is when it's growing the fastest. Okay, so what is the population growth rate when it's growing the fastest? Once again, we know dn dt is equal to the growth rate. Okay, I tell you that the growth rate is 0.27 times the number in the population, right? So we know 7,500 butterflies times 1 minus, we know that this whole thing is 0.5, but just to be clear, 7,500 butterflies over 15,000 butterflies. Okay, and if we bash these numbers together, we get 1,012.5 butterflies. Okay, so really what we want to round to the nearest whole number is 1,013 butterflies. And again, what this is actually telling us is 1,013 butterflies are added to the population when it is growing the fastest. Again, I hope that that cleared up any misunderstandings about this particular type of problem.